All right, good morning, everybody. I appreciate everybody getting up somewhat early. For us East Coasters, it's actually about lunchtime, so will try not to keep you too long. So what I'm going to talk about today is specifically the volatile analysis portion of Resource Prospector. And so, of course, before I talk about the volatile analysis, I have to give you a big picture of what the overall mission includes and what our limitations are. And this helps guide and understand what some of our requirements are at the lower level for volatile analysis. So we have two main missions up here, or two main goals in our mission. We are to characterize the nature and distribution of the water and volatiles in the subsurface polar region. And we're also going to demonstrate ISRU processing of lunar regolith. So this really is a marriage between science and ISRU. We have both goals. We're going to work together to achieve both goals as we move forward with our science. So a couple of things that I want to point out in our specifications here. Unlike the previous talk, our mission is 6 to 14 days right now, unfortunately. We're not going to be here for 8. I would love to be up here in 8 years talking about all the science we're going to get on the lunar moon, or on the lunar surface, but I don't think that's going to happen. So this short mission really drives a lot of our requirements. A lot of the traditional ways you do volatile analysis won't work for our short mission duration. We are about 300 kilograms for our rover and payload mass, and we're limited to about 300 watts. For our overall project timeline, we are in our level 2 requirements lockdown, so we are getting we're refining our requirements so we can nail down what we're doing for our instruments at the lower level. So the toolbox, many of you have seen this slide before. This is Tony's slide on what toolboxes, what we have for Resource Prospector. And what we start with is the rover. So obviously, if we're going to explore the distribution of water and other volatiles on the moon, we have to be able to get around the moon. So we have our mobility system, cameras, and we're looking at the surface interaction as we rove around the surface, the polar surface of the moon, to get as much information as we can as we explore the area. Then we're going to do our prospecting work. And this is done by the neutron spectrometer subsystem and the near-infrared spectrometer subsystem. And so the neutron spectrometer is looking for water-equivalent hydrogen. It's kind of like the bloodhound of our system. So it's sniffing out the hydrogen. It goes about 1 meter deep, and that's what we're looking at in terms of understanding where the water is on the surface. The near-infrared volatile spectrometer subsystem, you'll hear later about more about that. It's looking at surface water and OH detection. And so this is for samples that have been brought up from the dirt, or looking at what's on the surface of the lunar regolith. Once we find a hotspot after we are prospecting, we're going to go and look at sampling. And so for that sampling, we have a drill. There is a presentation on the drill. This over here is my little pop-up ad that you see on the TVs. So if you want to know anything more about here, you can't click on this. You have to actually go to the posters or the presentation. So we're still a little old school here. But for the drill, we have an augering drill. And we have the ability to bring up a sample from any depth within that meter. And we either dump it on the ground to look at it with a near-infrared spectrometer, or we take it and process it. And so I'm going to spend most of my time talking about the processing and analysis tools that we're using. And so this is the oxygen volatile extraction node, or the OVEN subsystem. We spent a lot of time on acronyms. This project's been going on for a while. So this is looking at the volatile content by warming, excuse me. And we're also getting information on total sample mass with this hardware. And then we come to the Lunar Advanced Volatile Analysis, or LAVA subsystem. I will say that this name came from the fact that we've done several field trips in Hawaii, field demonstrations, so we wanted to pay homage to our roots and all the work that we've done in Hawaii. So the LAVA has an analytical volatile identification and quantification. It has a GCMS in there, and we are responsible for measuring water content of the regolith down to 0.5 weight%. And so we are also interested in characterizing volatiles of interest below 70 AMU. So it's not just the water we're looking at, it's all the volatiles, but water is our primary area of interest. So many of you have seen this rover. This is the RP-15 mission in a year. So we took this ambitious challenge of creating a hardware assembly that went from all the way from the rover to the instruments inside, put it all together, and did the ConOps for an integrated mission, and this is in the JSC Rock Yard. So we had command stations at KSC, we had them at Ames, at Honeybee, and then we actually went and performed the overall mission for volatile analysis. So we did the prospecting, we did the volatile analysis. I will point out here that we are a solar-powered mission, so we do have limitations in terms of how long we're going to live. And because we're a solar-powered mission, we have these great wheels right here. These are articulating wheels, and what that allows us to do is always stay and orient ourselves so that solar panel is always looking at the sun. And so one of the things that actually allowed us to do, and was a happy side effect of that, is if we get caught in very deep soil, we are actually able to army crawl out of that soil because of the articulating wheels. So it was a design that was needed for the solar power, but it also has some great effects when we maybe get into some trouble with some soft regolith. So I just wanted to show this information. This is the volatile analysis system that we performed during RP15. So here in the, we have the oven subsystem. So we have this crucible that is in the reactor station. It's heating the sample up. We can see here as we're heating the sample up, we're building pressure. And it might be kind of hard to see, but this is the GC interface right here. And what we have is increasing water peaks as the gases evolved from the lunar regolith. So this is really what we expect to see on the lunar surface as well. However, we're also going to have a mass spectrometer. So unfortunately, we were operating in this ambient environment, and we have this air around, so we can't operate the mass spectrometer very easily. So the oven is the oxygen volatile extraction node. So it has multiple functions. It has an arm here in the center that is used for articulating the crucible and the sample. It receives the sample from the drill. Right now, we're taking about a 12 cc sample from the lunar regolith. And so we're measuring how much regolith we're going to analyze by volume right now. And so we collect that 12 cc's that is delivered to us from the drill. We go over and we weigh it here in our weighing station. Then we put it in our reactor subsystem or reactor station. The reactor seals it, heats it, and drives off the volatiles. Once we're done with the volatile analysis, we're able to dump the regolith, and we can actually reuse that crucible. So right now we have reusable crucibles in our system. So the oven subsystem team has been busy on doing a lot of the trades and understanding how the science is really driving the hardware requirements. And so we've completed testing to understand the temperature distribution of the regolith during the heating and the volatile extraction. So this is a really important thing both for science and ISRU. From a science perspective, we want to understand when the volatiles come off because that gives us information about how they're bound to the surface. From an ISRU perspective, we're interested in how much energy do we have to put into that soil in order to get the resources out that we want to have. So, and we all know that regolith is a great insulator. So we have a 12 cc sample, which is a fairly large sample. So we put a lot of energy into understanding what the best configuration was for the heaters and for the temperature profiles so that we could minimize the distribution of the temperatures during our volatile analysis. We also completed testing of the required sealing forces. Regolith and seals don't really go together, and so we wanted reusable seals. We've done a lot of work on trying to understand what the best way is to seal this subsystem, to isolate the sealing surfaces from the heating surfaces. So they've done a bunch of tests, and they've come to a design that minimizes the dust contamination on the seals, and so we're able to go forward and capture those volatiles as we heat up the system. We still have a few trade studies that we're working on, and a lot of these are being driven by the science team. And we're working closely with the science team to understand what our requirements are so that we can make acceptable trades for these hardware studies. One of them, and you'll hear later about this in Julie's talk, is understanding volatile loss while we're drilling and transferring the sample. We obviously want to minimize that volatile loss. So one of the ways that the oven subsystem is addressing that is looking at chilling the crucible. Obviously, this is going to add complexity and add hardware. However, it could reduce the sublimation losses. So that's one area that we're looking at for a trade for the oven subsystem. We're also looking at the weighing in the dump stations. And given our timeline, we are not sure if we're really going to have enough time for more than 4 samples. And we're understanding the trade between carrying 4 crucibles versus having a reusable crucible. So that is an ongoing trade study. We're also looking at the weigh station to understand. Now that plays into our overall accuracy requirements. We right now have a known volume, and that's 12 cc's. However, if we don't have the mass, then that adds to our inaccuracy that we're doing, so we're going to obtain. So we're trying to work with the science team to understand what our real requirements are and if that is a worthwhile trade. So the last 2 things here are we're looking at an integrated RTD in the crucible. This is something that scientists and I would really like to have. However, it definitely adds complexity when you have all of these moving parts and you have this abrasive regolith coming in and out. So that is something that is still under consideration. And finally, we're looking at an active versus passive gripper for the hardware. So now that we have the oven subsystem that has heated the regolith and evolved the sample into the gas phase, now we have to quantify it and analyze it, and that's done by the lava subsystem. So the lava subsystem is a gas chromatograph, a mass spectrometer, and a fluid subsystem. And you can see here, this is the GC module, this is our mass spectrometer, and this is our fluid subsystem. So the volatiles are transferred from the oven subsystem, from the headspace in that reactor, into the fluid subsystem over here, and then we measure the temperature and the pressure. And we're controlling the temperature of all of this. All of this is kept at 150 degrees C because we need to prevent condensation. If we allow anything to condense, we're not going to be able to accurately quantify it, so we need to keep everything in the volatile phase. So our gases of interest are here. They were from the L-cross data, so we're looking specifically at masses 1 through 70. And the last thing I want to mention here is that after we evolve the water and we quantify it and identifying it, we're actually going to condense it on the water droplet demonstration. And what this does is demonstrate that we're going to be able to have the water in a storable form, but it's also really a lot for outreach. So all of us in this room can probably get very excited about the squiggly lines that tell us there's water up there, but when we're going home on the airplane and we're trying to explain to the guy next to me what I'm doing, it's easy to show him a picture of water from the moon. And seeing that picture of water on the moon is really something that we're trying to hold on to in our mission so that everybody can relate to that. All right, so I'm going to breeze through this real quick. And so this is how we're doing volatile analysis and identification and quantification. And so after we do the near-surface assay and locate the sample of interest, we transfer the regolith into the oven seals, it heats it up, and then that gas is transferred into this right here, what we call the surge tank, and it's about 100 cc volume. We know the volume, we know the temperature, we use PV equals nRT, the ideal gas law, to figure out how many moles are there. It's a very simple approach to quantifying. Once we know how many moles of gas are in there, then we're going to analyze it with the GCMS so we know what percentage is water versus other components. So for the instrumentation, we are a Class D mission. We are using the modified COTS approach. And so we have an Inficon Fusion Micro GC module. It's got a single plot Q column that separates the inert components from the CO2 and water. We have an isothermal operation. And again, because we're 6 to 14 days, although it would be great if I could take 2 hours for analysis, we've got about 2 or 3 minutes per sample. So this is why we're doing modified COTS. We've looked at all the other missions and there was nothing that really fit our timeline and our needs. We have an Inficon Prospector MPH, which is our mass spectrometer. If you want to know more about the mass spec trade that we did last year, please come and see me. We have an extensive trade study that we did with lots of data analysis. It's about 3.5 kilograms, and it takes about 20 watts to operate, and it is a quadrupole. So I want to end here with talking about this water calibration data. So we've calibrated the system from about 1,000 RPM all the way up to 20% water. And that's a pretty big range that we're talking about. And then you're also talking about water. So most of the time, if you're a chemist and you call a company and you say, hey, I want to put water in your mass spec, or hey, I want to put water in your GC, they don't look at you very favorably. They go through extreme lengths to try and keep it out of there. So we've actually been able to modify these to meet our needs and actually quantify the water, and we've got the data to prove that. So as I'm getting kicked off the stage here, on my last thing, I know, gentle nudge. So I will want to say, I'll just end with this. 1,000 ppm, I know some of you are in the audience saying, my instrument can do much better than that, I don't need, you know. So one of the things that we have to understand is the concentration that you have to analyze in the volatile phase is not directly, cannot be directly extrapolated from how much is in the dirt. Just because it's a small amount in the dirt, if water is the only thing there, you have to analyze 100%. And so our instrument having an analytical capability of 1,000 ppm is actually an order of magnitude higher than what we need to do based on our assumptions. So if you have any more questions or comments or want to know more about the instrumentation, please let me know.
Thanks so much. Appreciate that.